Let's talk about how to insert a new item into a list when we want the list to be in a particular order. So we want to insert a new item in order in a particular list. So for example, let's have our list of integers. Let's say we've got 5, 10, and 15. We want to keep this in sorted order, low to high. And we want to insert a new value, 12. Well, we have to figure out where does 12 go in this order. It goes between 10 and 15. So we need to create a new node and insert it into the list at the right place. So how do we do that? We traverse the list to find the first element whose value is greater than or equal to the thing we want to put in. So that would be here. But we also need the previous element to point to the new value, right? It's not enough to know this address. We need that for new to point to that address, but we also need to change this node. So what we do is we use a following pointer. We use 2 pointers as we traverse the list, and one lags behind, so that when we find the right node, we also remember the previous node, because we need both of those addresses to insert. Let's see how this works. So here's our list, 5, 10, 15. I'm going to assume for now that the value that we're going to insert is in the middle somewhere in between here. We'll cover the other special cases shortly. So what do? First thing we do is we create a node. So new equals malloc. We set the value. We initialize this to be null, right? Now, you always need to worry about the special case of an empty list. So if we insert something into an empty list, then the new list is going to be the new node. There is no sorting order. So we can just put a little special case here. If age is equal to null, we can return new and we're done. So that's why we initialize to null, because we just return new, null is set, data is set, so we're good to go. We don't have to worry about the rest of it. Okay, so taking care of the empty list problem. Now let's assume we're going to put it in the middle. So now we initialize 2 pointers, P, we initialize to be H, which is the first pointer here. And then prev is our previous pointer. We declared it up here. Prev is our pointer that's going to follow behind P as we go through the list. So there's nothing before the head of the list, so we initialize prev to be null. Okay, so we have P here, and we have prev null. Now we traverse the list looking for an item that's greater than or equal to 12. So while P data is less than val, which is 12, right, we're going to move on. So by moving on, we don't just move P, we also have to move prev. So be sure that we assign prev equals P before we do P equals P next, because once we've done this, we've forgotten what P used to be. And this is the whole point of having prev here. So as we move, this loop traverses the list, but it moves both pointers. When P reaches here, P data less than val fails. Prev points to the previous one. So these are our 2 pointers that we need, and we simply adjust and make prev next equal new. So we make this point to here, and new next equals P. We make this point to here. Then we return H, the original head of the list is still the head of the list, and we're done. Okay, so that's the basic insert code. However, there are a couple of special cases that we need to worry about. Number one, what if we insert our value here before the head of the list? And number two, what if we have to insert the value at the tail of the list? Let's look at those special cases and see if there's anything we need to change about the code. Okay, so here's a case where we're inserting 3. Okay, 3 is going to go before 5, obviously. I left out the part about creating a new node. We've done that enough times. Don't need to see that every time. We initialize P equals H, and we know the list isn't empty, right? We've accounted for that up here. P is H, so P points here. Prev is null here, okay? While P data less than val, that's never going to happen. The very first thing we look at is greater than val, so we stop right there, okay? Now we have a potential problem because what we did before after the while loop is we did prev next equals new. Well, prev is null. So if we do prev next, segfault. But we don't want prev next to be equals null. We want new, we don't want prev next to be new. We want new to be the new head of our list. So we want H to point to new. So that's what we do here. So we detect this case. If we've gone through this loop, we found something where P's value is greater than new's value. Okay? If we're done with that loop and we see that prev is equal to null, that means we didn't move P at all. And that means that the thing that matched here was the first thing in the list. So this is how we detect this special case of inserting at the head of the list. H equals new, otherwise prev next equals new. And in either case, we do new next equals P. Right? This goes to here. Whether it's over here or whether it's here, this is always the case. And we return H. We set H equals new here, we return H. Now this is the pointer that we return instead of the original head. Okay? So this is the special case that we had to add for the case where we're inserting at the head. What about inserting at the tail? How does that work? Do we need to do anything special? Well, if we've got 20 that we're adding, it's greater than 15, so we move our pointer. P goes into here. P15, P data is 15, that's not less than 20. That is less than 20, so we go ahead, and then we set P equals P next, so P is equal to null. Okay. The problem is we're still in our loop because we haven't found this condition P data less than val to be true yet. If we have this loop and then we say P equals null, and then we say P data less than val, segfault. So we have to put in a condition in the while loop that says as long as P is not equal to null, then we'll check for P data less than val. If this is true, if this is false, so P equals to null, then because of the shortcut nature of the logical AND, we won't evaluate that code. So if it is null, we don't get the segfault here. This is the great advantage of using the logical AND or the logical OR in these cases. Okay, so P is equal to null, we fail, and here's our situation. Prev points to the tail of the list, P is equal to null. Well, we still have our test. Prev is not equal to null, so we don't do H equal new. We do prev next equal new, which is exactly what we want. New next is equal to P. Well, P is equal to null. We want this to be null. It's already null because we initialized it that way. But what I'm saying here is we don't have to have a special if test to make this happen correctly. Because P is null, we want new next to be null, and we're done. So the thing we added for this case is you might call it a guard condition, right? We conditionalize on P being non-null before we check its value. And with those changes, with this special case, with that special case, the entire insertion code works, whether it's at the front, in the middle, or at the end. And as a matter of fact, this case for dealing with the end, these two cases together also deal with the empty list case. So if you wanted to take out that special case of H being null, you could, but it's not necessary. Okay, so that's the insertion code. Let me point out then that probably the easiest algorithm for sorting a list, let's say you have a linked list and you want to put it in some sorted order. Well, we know how to insert an item into a new list in sorted order. So we can just create a new list that will be the sorted list. We create it as empty to begin with. Then we step by step look at the first element of the original list. We remove it from the list and we insert that node into the sorted list. We don't have to create a new node. We have a node. We're just putting it in the right place in the sorted list order. Right? So step 2 and 3. Step 2, remove the head of the original list. Right? We're going to pop it off. We're going to insert it into the proper position of the sorted list. We're going to keep doing this until the original list is empty. Once we've done that, our sorted list has all the same nodes in it. The pointers have been changed so they're in sorted order, and we can return that head of the sorted list and say, here's your sorted list. So this is, in my opinion, the easiest algorithm to use for sorting a linked list.